Hi, welcome back. Today we are going through lesson 9.6, which is all about graphing the reciprocal functions, which you'll see kind of how those work in a second here. So when we graph any sort of function, we start with what's called the parent function. So in the parent function, we're looking at the function before we transform it at all. It's the most basic function. So for reciprocal functions, that function is the f of x equals 1 over x. So reciprocal fraction, meaning the opposite fraction. So we're taking what used to just be x and now we're making it 1 over x. So as we think about the function 1 over x, we have to kind of start thinking about what values we can plug in and get out from it. So when we think about 1 over x, in math, there's always one number that we're never allowed to divide by, and that's 0. So when we think about x can be any number except 0. So when we think about the domain of this function, we'd say that the domain is all x values except x cannot equal 0, because again, we're never allowed to divide by 0 in our math. If we think about what that means in terms of the graph, that means that our x value can never be 0. So in that case, all of these x values of 0 are not possible. So we draw this dashed line and that represents the asymptote. Those are the values that the x can never be. So we would say that since x can never equal 0, that line is x equals 0, and that's a vertical asymptote. And then thinking along the same lines, if we divide 1 by any number besides 0, so positive, negative, fraction, whole number, integer, doesn't matter, we are always going to get 1 over some number, which is not going to equal 0 either. So our range, the outputs that we can get for this, are the same as the inputs. We can get any y value except y cannot equal 0. So since y cannot be 0, we also have an asymptote going straight across where all the y values are 0 in our graph. And we would have a horizontal asymptote there at y equals 0. So remember, asymptotes are all the values it cannot equal, so that's how they line up with the domain and range. So our graph cannot equal any of those values, so we know that those asymptotes are there on our graph. Now we're going to kind of figure out what the rest of our graph looks like. So in this case, if we plug in some x values, so we just pick some x values here to kind of plug in and see what happens. If I plug in -1 for x, we get 1 over -1, which would equal just -1. So on my graph, if I go to -1 and down to -1, I'd have a point there. If I plug in a half, I get 1 over a half, which if we think about flips that 1/2 upside down, that becomes a 2. So when I plug in a half, I get out a 2. So if I go over to a half up to 2, I would just have, if I plug in 2, I would just have 1 over 2, which is of course a half. So over to 2, up to a half, puts a point there. So we could continue plugging some points in. The general shape of this curve is going to come down and approach those asymptotes, but never touch them. And then the same thing's happening in the negative quadrant, the third quadrant over there. So it's approaching the asymptote, comes down, curves, and approaches that. So when we have this graph with two curves kind of in both corners, we call that a hyperbola. So that is the name of our graph there. So that is the most basic reciprocal function we can graph. And so what we're going to do now is we are going to use that to kind of start figuring out how we do some transformations with this. So we're actually going to start on the next page and then come back and fill in the bottom of this page in just a second. So all right, so if we look at the next page, we can see all of the different transformations that are going on. So we're going to kind of go through these individually. The graphs are already there for us to kind of help us see it all, but we can use that to determine some things that are going to come up here. Okay, so the first thing we have is our translation. So translation means take the whole shape of the graph and move it. So move it up, down, left, and right. So first we have vertical shifts. So in vertical shifts, we can go up or down. So you can see it on that green graph, it's shifted up, and that would tell me that I have added a positive number up there on the end of my reciprocal function. If I want to shift down, I would do the opposite. So you can see in the blue graph, we've shifted it down 4 because we were subtracting a number after the reciprocal function. So to shift vertically, up or down, we either add a number on the end of our function or we subtract a number at the end of our function. And we'll talk in a minute about what that does to the asymptotes and whatnot, but you can kind of see that horizontal asymptote is moving. Okay, so then we have our horizontal shifts. So horizontal, of course, would be left or right. Shift it left or right, you can see that we are adding or subtracting a number in the denominator with the x in our original function. So to shift it left, you'll see that we've added 3, and that's because in the parent function, it's x minus h is the letter we're going to use for that. So if we subtract a negative, that becomes a positive. So we're actually, in this case, subtracting -3, so that we would write that as x minus -3. And since it's subtracting -3, that's what shifts it left. That's what moves the asymptote to -3. And then same thing on the shift right. In the denominator of the fraction now we have x minus 2. That 2 is positive that I'm subtracting, so it shifts right too in the positive direction. So horizontal shifts are a little tricky because they're opposite of what you would think they might be. All right, so those are all the translations. Then we have 2 other transformations that we might do. So the first one is a dilation. So in a dilation, we are either stretching or compressing the entire curve, or both entire curves. So when I think about this one, a dilation is going to multiply by some number out in front of the reciprocal. So it's multiplying basically the numerator by some number. If that number is bigger than 1, it's going to stretch all the points. So think about vertically stretching, it's stretching the y values away from each other. And if we're compressing, then that means that our a value is between 1 and 0. So that means that the a value is some fraction or decimal between 0 and 1, still positive, but it's going to compress it or push it closer to that x-axis, pull it closer to that x-axis. So you can kind of see in the graphs in the dark blue, or in the purple and the light blue down there, you can kind of see in the stretch, I always think of it as stretched a little bit further away from that origin, whereas the compression is pushing it a little closer to the origin. All right, and then lastly, our last transformation that we're going to talk about is a reflection. So when we have a reflection, we can reflect it either over the x-axis or we can reflect it over the y-axis. So when we reflect it over the x-axis, we do that by putting a negative out in front. So you can see that my curves flip from the first and third quadrant to the second and fourth quadrant. Now we can also reflect over the y-axis, which you'll notice looks very similar. We can tell by the equation that we've made the x values negative, so it's flipped those x values, but it looks very similar. Still now flipped into the second and fourth quadrant as opposed to the first and the third. So we really use the equation to figure out which reflection has happened because it's hard to tell from the graphs which one it is. All right, so now that you have some ideas about that, we're going to go back to that first page and we are going to fill in some of the key information about those transformations. So we know from before that the parent function is 1 over x. If we're going to transform it, we can use some key letters to kind of indicate that. So each transformation has a letter that it's stands for it. So when we write the transformations all out, the a value, remember that's the stretch or the compression, and the reflection, that goes in the numerator there. And then on the denominator, we still have the x. That x has to be in the denominator. That's what makes it a reciprocal function. And then remember, we're dealing with our horizontal shift here. So that is in the denominator with x. We use h for that. And then we had our vertical shift, which comes after the function, and we represent it with k as the letter for it. Okay. So from those transformations, we should remember, hopefully from the last page, that the h value represents the horizontal shift, like we talked about, moves it left or right. And when we shift it left or right, that is going to affect the vertical asymptote. So for the vertical asymptote, when it shifts left or right, it also reflects that same h value. The k value is the opposite of that. That represents the vertical shift. So that would be going up or down, depending on the type of number we plug in there. And when we shift the whole graph up or down, that's going to affect the horizontal asymptote. So that horizontal asymptote is going to be at y equals whatever number we've shifted. All right, and then we have that last letter A. That A represents our reflection. And when the A becomes a negative, that's going to reflect everything across the x-axis. Remember, in order for it to reflect across y, we'd have to make the x negative. So the A only controls the reflection over the x-axis. If it's negative, that A value also tells us about that stretch or compression. So remember, if A is bigger than 1, that is a vertical stretch. And if the A is between 0 and 1, so it's some fraction or decimal less than 1, but still in the positive numbers, that's a vertical compression. So that shifts it or shrinks it closer to that origin value. So those are all the transformations that we need to know. We need to know translations, so moving it up, down, left, and right. We need to know dilations, pulling it further away from the origin or closer, and reflection, so flipping it into the other quadrants from where it was. So we're going to practice with that a little bit. So on this page, we are going to use all the stuff we've talked about in order to transform our functions. So for this first set, it's using what we've just talked about with the transformations to write the equation. Okay, so for A here, we have a horizontal shift 4 units right and a shift 5 units up. So remember, a right shift is going to change my function by putting a value down with x. So remember, if it's to the right, I write it as minus positive 4. So always minus after the x, and then the sign on the actual number tells us if it's going right or left. So positive 4 is to the right. And then to shift it up 5, we add 5 on the end of our function. For part B, we want a reflection across the x-axis. So remember, that's going to affect that a value in the numerator. And then we have a shift 3 units left. So my function for this one, again, to reflect over the x-axis, we make the a value -1. And then to shift it left 3, we're going to subtract a -3, which you can write as minus -3, or you can write it as positive 3. And that'll take care of those two transformations. For part C, we want a vertical stretch by 2. So remember, that's going to be the a value. And then we want a shift 4 units down, which is going to be the k value. So my function would have a stretch of 2. So my a value in the numerator becomes a 2. There's no shift left or right, so just an x in the denominator. And then to go down 4, I'm going to subtract 4 from the end of my function. This last one, instead of giving us the transformations, we have to figure out the transformations given the asymptotes. So if my vertical asymptote is at x equals 3, that means that it has shifted to the right 3. So this here tells me that I have gone to the right 3. And if my horizontal asymptote is now at y equals 1, So that means that it has gone up 1 because normally it's at 0. So from that, I can use that to determine what my function looks like. So they didn't tell me anything about a stretch or a compression or a reflection, so it would just be a 1. To go right 3, I would subtract positive 3 in the denominator. And then my horizontal asymptote shifted up 1, so that would be a positive 1. Okay, so that's some practice on writing the functions just given the transformations in writing. Now we are going to graph some functions and then make sure we understand how to put the transformations on the actual graph. Okay, so for example, E here, we have the function 3 over x minus 2. So what I usually have to do to think about these is I have to think about what transformations are going on. So that 3 on top tells me that it's a stretch of 3. And then the minus 2 on the end tells me that it has shifted down. Down 2. So what I know from a shift down 2 is that my horizontal asymptote has gone down to -2. So it's now at -2. I don't see anything about a shift left or right, so my vertical asymptote has stayed at x equals 0. So I can go ahead and graph those on my graph to make sure I have those in the right spot. And because of those asymptotes still being at 0 for the x, that means my domain is still all the x values except x cannot equal 0. And my y values now can be everything except -2. Because the 3 over x cannot equal 0, there's no possible way for that to happen with a 3 in the numerator. So since I can't do 0 minus 2 in this function, I'm never going to get -2 as an answer. I can get really, really close, but I'm never going to actually get -2. So that's what my function looks like. And then I know, depending on what your teacher requires, some teachers just want you to sketch kind of what's going on. So since it's a stretch of 3, it's pulled away from 3 a little bit. Other teachers want you to get specific values. So you kind of have to listen to what they say, but in this case, some key points. I know that if I plug in an x value of 3, I'm going to get 3 over 3, which is 1, minus 2 is -1. So I can get some kind of key points here and start to make points that way if I need to. I also know that I can plug in 1 easily because 3 divided by 1 is 3, minus 2 is +1. So 1 would be right there. So you can start to get a feel for what that stretch kind of does in our function. Same thing in that negative region. I can plug in a -3 easily because 3 divided by -3 is -1, minus 2 is -3. So -3 kind of looks like that. We can get a feel for what that one looks like. So our graph would look like that. All right, for graph F here, I can see that I have a stretch of 2 again in the numerator. I can see that I have a shift right 3 in the denominator. And I can also see that it's shifting down 3. So the shift right 3 is going to change my vertical asymptote to x equals 3. And the shift down 3 is going to move my horizontal asymptote to y equals -3. So I can graph those. X equals 3, y equals -3. And then that will tell me my domain. So my domain in this case, I cannot plug in a +3 to the denominator. If I plug in x equals 3, I'm going to get a 0 in the denominator, which is not allowed. So the domain in this case is that x is all numbers except x cannot equal 3. That would give me a 0 that I'm dividing by, which is not possible. So x cannot equal 3. That's why the asymptote is there. And for my range is going to be all the y values except I cannot get a y value of 3. That will never happen. I cannot get a y value of negative 3. That will never happen. Okay. So again, kind of depending on what your teacher expects from you, you can either find some key points by plugging in easy numbers to figure out. So in this case, some easy numbers. If I wanted to plug in 4, that would give me a 1 in the denominator because 4 minus 3 is 1. 2 divided by 1 is 2, minus 3 is negative 1. So I can see that 4, I'm at negative 1. Another easy one would maybe be 6. Another easy one would maybe be 5, because 5 minus 3 is 2. 2 divided by 2 is 1, minus 3 is negative 2. So I can kind of get some ideas here about what's going on. We do know that there's that stretch of 2, so it's pulled a little ways away from where those asymptotes meet each other. So you have an idea of kind of what's going on there. All right, so let's look at our last two here. So for g, we have a function of 1 over x minus 2. So that is a shift right 2. And then I have a shift, or a k value on the end of plus 1. That's going to be a shift up 1. So that tells me that my vertical asymptote is at x equals 2. So my x value cannot be 2 because that would cause me to divide by 0, which is not allowed. And my horizontal asymptote, the output that I'm never going to get, is going to be at positive 1. My domain is all the x values except x cannot equal 2, would cause that division by 0. And my outputs, I can get any output value except 1. So y cannot equal 1. All right, so looking at some key points here that I could probably use. 3, if I plug in a 3, that would give me 1. So 1 divided by 1 is 1, plus 1 is 2. So my input-output pair's there. So if I go over to 3 up to 2, I have a point. And then let's try a negative 1. So what would give me negative 1 in the denominator would be positive 1. So 1 minus 2 is negative 1. 1 divided by negative 1 is negative 1, plus 1 is 0. So I know that over at 1, I'm at 0. So you get a feel. There's no stretch or shrink here, so it's pretty close to where those asymptotes meet. Right, and then our last example of graphing here is h. So we have a function with a negative 4. So that negative tells me that it's a reflection across x. It's got a stretch of 4. And I have a plus 2 in the denominator with the x, so that's going to tell me that it goes left 2, because it's subtracting a negative 2. So left 2, that would affect my vertical asymptote. So now my vertical asymptote would be at x equals negative 2. So drawing that on my graph. My horizontal asymptote, there's no k value on the end, so it's still at 0. So we've got those. That tells me then that my domain is all the x values except x cannot equal negative 2. And my y values, I can get any output except 0. Okay, now this has a stretch of negative 4, so we have to think about that when we're making our sketch. It's a pretty big stretch away from where those asymptotes meet. So maybe thinking about some key points here that would be easy to use. If I plug in 0, 0 plus 2 in the denominator, that's 2. Negative 4 divided by 2 is negative 2. So at 0, we're down here at negative 2. Remember, it's also reflected. So instead of being in kind of the first and third quadrants areas, now it's in the second and fourth. What else would be easy to plug in? Maybe a 2. Because in the denominator, I have 4. Negative 4 divided by 4 is negative 1. So at 2, down here at negative 1. So it's stretched out there, kind of like that. And then the top left part, similar kind of stretch going on looks something like that. All right, so that is how you graph the reciprocal function. We'll see you next time.